Good afternoon, everyone. I'm here to present our research on augmentation and transformation for nighttime cloud segmentation in all sky camera images. First, I would like to introduce the background of our research. Our work addressed a critical challenge in automatic telescope observation systems. This system using all sky camera to capture the sky information and the cloud location. And these all sky cameras will using the fisheye lenses to capture image. An observation routine typically involves pointing the telescope at a target astronomy object for a set of time. However, the challenge we faced during nighttime is that the system cannot reliably discriminate sea cloud obstruction from clear sky. The telescope will point to an obstruction area of sky and will result in waste of valuable observation time. Therefore, our objective is to develop an algorithm that accurately segments the obstruction area from clear sky in target area. The target area is a white circle in the example image. And since the obstruction mainly caused by the sea clouds, our task is to perform robust cloud segmentation at night. Next, look at the related work. I will briefly outline three state-of-art models we evaluated. First, the cloud segnet, which uses a convolutional block to perform segmentation task. Next is UNet, which is a classical segmentation model. And the last is ACLNet, which is the most recent one and use attention mechanism to enhance the performance. It's important to know that all these three are primarily designed for daytime segmentation. This highlights a significant gap in the research. We lack high-quality nighttime benchmark datasets. Existing datasets are mostly daytime, and the few nighttime ones are usually featured brighter dusk scene, like the swing seg on the right. As shown in the image from the Mountain Stromolo Observatory here in Australia, real-world nighttime data is very different. We face darker backgrounds, unbalanced illumination on the clouds, and insufficient contrast between sky and clouds. Factors like the moonlight, lens flare, and fisheye distortion make it difficult to apply the daytime model directly to this domain. To address these challenges, we propose a specific augmentation and transformation pipeline. Since we lack real-world training data, we simulate these conditions using the daytime dataset SwimSeg and the nighttime dataset SwimSeg, which is the right part. Then our pipeline using two main strategies, image augmentation and style transformation. For augmentation, we simulate real-world interference, the night glow, which is simulated through the Gaussian blur, and which the night glow is caused by the city light pollution, and the lens flare, which is to simulate the lens flare from the camera caused by the moonlight. For the transformation, we transform the day and dusk image into nighttime style, and we are also simulate the distortion caused by the fisheye camera. Here we visualize these techniques. First, the cyclogram converts daytime image into synthetic nighttime image that matches the style of our observatory. You may notice that the bright section on the clouds. This is intentional to simulate the moonlight illumination. Next, we apply Gaussian blur to replicate the night glow, enhancing the brightness in the background and the clouds. Well, we also insert the lens flare at random position to ensure the model is robust against these common artifacts. Finally, the fisheye transformation is crucial. Previous research shows that the model trained on standard image fail when applied to distorted wide-angle inputs. We also generate complex situations that combine all these transformations to simulate the most complex scenario. Finally, we show the flowchart of the data augmentation and transformation pipeline, which shows each step of the transformation and augmentation, and finally produce out the night cloud simulated dataset. Now let's go to the experiment part. We train all the three models shown in the related work using the data from the augmentation pipeline, and the ACLNet delivers the most robust and accurate performance. Hence, we choose the ACLNet as a baseline model for the further test. Then we conduct two studies, an ablation study for the pipeline and an interference evaluation. In the ablation study, we isolate the impact of each augmentation step, and the method is that we train the ACLNet, which is a baseline model, using each dataset from each pipeline stage. And from the result, we can observe that the day-to-night style transfer provides the biggest boost in the precision, and along with day-to-night transformation, sky glow, and the lens flare, which gives the best performance. Also, then to test robustness, we test the model's performance on different interference. We try to evaluate the robustness of the model trained with pipeline generated dataset against each type of interference highlighted in the challenge part. Also, we are comparing the pipeline model, which is trained using our fully augmented data, against the benchmark model, which is the best performer from the ablation study trained on the limited data. And the result shows that while pipeline model had slightly lower precision in simple scenarios, it achieves significant higher recall in complex, challenging scenarios. For a telescope system, recall is crucial. Missing a cloud, which is a low recall, means telescope with time staring and an obstruction. Therefore, despite the slight trade-off in precision, the pipeline model is safer and more efficient for a specific application. Finally, we validate the model using real-world data since we do not have a pixel-level ground truth for real night sky. We use two methods. First, we compare our model prediction with cloud mask from Himawari satellites. Since each pixel corresponding to an area of 2 by 2 kilometer square, we take a 12 by 12 pixel region to represent the area captured by the camera and compute its average value. And from the results, we achieved a correlation coefficient of 0.36. While this indicates only a moderate positive relationship, it confirms the model is tracking the cloud coverage trend. Also, we found that the moonlight will significantly impact the model's performance. Second, human expert human verification is applied. We make prediction using the model on over 4,000 images from MSO sites and use them for human verification. We split this prediction into 4 different scenarios and give human 3 options to choose. And we find from the result, we find that the model performance is robust in clear and few cloud conditions. However, the model performance decline as the cloud coverage thickens. The model generally captures a cloud texture well from the expert feedback. But since the threshold is fixed, the unbalanced illumination will cause the model to ignore the darker cloud. This suggests that developing an adaptive thresholding mechanism is a key direction for future research. That's conclude my presentation. Thanks for your listening.